All right, looks like most everyone's here, so I'm going to go ahead and get started. So hello, good morning. I'm Jeremy. I work at Heroku. I am the Node platform owner. I maintain the build pack, I write documentation, I answer support tickets, and I sometimes come to conferences. And like that may sound like a pretty cool job, and most people think that until I tell them that like half my time is spent writing bash and debugging webpack configs from other people. So that's fun. But sometimes I get to come out and talk to people like you, and that's probably the best part of my job. So I wanted to bring up a subject that's sort of been on my mind, and that is types. Some of you might be like me, or like I was a couple months ago, and when you hear the phrase type system, your kind of brain goes back to Java, and you think like, oh, foo equals new foo. It's so repetitive. There's all this ceremony. And speaking for myself, I never really wrapped my head around the patterns that you see in like heavily object-oriented languages. Like I never knew when to make a factory or a singleton or an abstract factory bean Boolean thing. Like it just never really clicked in my brain, and it made me feel kind of dumb. So when I came to JavaScript and I came to dynamic languages, it felt like taking shackles off. Like there was no ceremony. I could just throw data into objects or maps and then pass it around to functions. Like everything was objects and functions, and I could wrap my head around that. I could just focus on getting things done. But then sometimes you would make mistakes or a typo, or you'd change something and you forget to update some file on the other side of your code base. And you add a new feature, and then things would blow up when you ran your code. You would get undefined is not a function, or length is not a property of on undefined. And that sort of felt like your fault. Like you forgot to handle the case. Like you were the one that mistyped it. You didn't think everything thoroughly through. So you fix it. You write a test to make sure it doesn't happen again, and you move it on. But it's sort of worth it for the productivity, because you don't want to go back to trying to figure out if you need a factory or a singleton or whatnot. But in the past few years, I've started to notice an increasing interest in typed languages. You have languages like Elm, which promote no runtime errors, and that sounds like a really nice feature to have. It also has really excellent error messages, and it's focused on user experience. And you have Mozilla has this language called Rust, and it's rewriting Firefox piece by piece. And though it's heavily influenced by C++, it has some really interesting guarantees around concurrency that it enforces through its type system. And my own meager attempts at concurrency in C++ left a lot of scar tissue, so that sounds really cool. And then the React community is starting to talk about this reason thing. Under the covers, it's really OCaml with some new syntax, but like, isn't that some academic language? Like, I write web servers. I'm not trying to get a PhD. And even if you ignore these three, like, it seems like most of the new languages that are sort of being talked about have a type system of some sort. Like you have Go or Swift or Kotlin or Elixir. And then even languages like Python and PHP are adding optional type systems. So it kind of seems like this is where our industry is headed. And it's like maybe there's something to this type system stuff, like, after all. And that's all well and good, you might say, but I do JavaScript. My team does JavaScript. Our app is written in JavaScript, thousands upon thousands of lines of JavaScript. We're not going to pick up some new tool or new language. So in that case, all hope is not lost. You're not out of luck. Flow and TypeScript from Facebook and Microsoft respectively are two projects that take JavaScript and lay a type system on top of the language we all know and love, or at least know and begrudgingly accept. And if you're sitting there thinking, well, we just spent a week trying to get our webpack config just right. We're not going to add another tool. No way. That's fine. And I hope that this talk is going to help you see what that trade-off might be, or why it might be valuable to consider adding this. So none of these type systems are perfect. I suggest trying both and seeing which one works for you. But this is a short talk, so today I'm only going to be talking about Flow and use Flow's syntax, because this Flow is the one that I have personally used in anger. But everything that I'm going to be saying today also applies to TypeScript as long as you're using version 2.0 and you have strict null checks turned on. So don't worry too much about the syntax, the differences, or whether this one is better than that one. Just kind of focus on the ideas. So a few months ago, this was sort of my thinking. I was looking at these languages and realized they all have something in common. Namely, that they're all influenced by this language called OCaml, which is like 2 decades old and has been around for a long time. Rust and Elm both claim OCaml as an influence. The first compiler for Rust was actually written in OCaml before it became self-hosting. Flow is still written in OCaml. And Reason is quite literally OCaml in new syntax and like a pretty bow. So then we have things like Rust. Pattern matching is inspired by OCaml's pattern matching. And now we're starting to see like C39 has a couple of proposals like pattern matching that to move these features into JavaScript. The recent pipeline operator proposal, OCaml had that too. Now, I'm not really a clever man, but when I see like this many smart people talking about something, it makes me feel like I might be missing something, or I want to like start to check it out. So I bought a book and I started learning OCaml. And I started to see why it had been so influential. Now I'm still learning OCaml, and I'm not really ready to talk about that. Like I haven't yet had the epiphany and risen to the clouds where I see everything writ large in golden script of lambda calculus. And I still could not explain to you for the life of me what a monad is. But when I went back to write JavaScript, it started to change how I thought about how I structured my code and how I used these type systems. Flow supported enough of the OCaml idioms that I started to write JavaScript kind of like an OCaml accent. And it changed how I thought about leveraging the type checker. And so I want to kind of talk about that. So this talk isn't an intro to Flow. I'm not going to tell you how to set up your editor or how to set it up in your project. But if you haven't seen type JavaScript before, I'm going to go over a couple of things so that all of us can be on the same page. So this is what a piece of type check JavaScript will look like. I'm declaring a variable foo, and it has the type string. Or we can leave it out. Modern type systems are actually really good at type inference. So here, it already knows that foo is a string. We don't have to tell it that. It can look at the code and what we assign to it and how we're using it, and it can infer that. You can also give types a name. It looks like this. This is the syntax. Here we're aliasing a string to maybe convey some extra intent to the user or whoever's calling our functions. This is the syntax you're going to use for declaring a function. It's pretty simple. This function takes in 2 numbers and returns a number, and you use the colon followed by the type name. Due to type inference in these languages, or in these type systems, you're mostly going to be adding your type definitions here at your function definition. Like inside the body and other code that you write, it's mostly going to look exactly like the JavaScript you're writing now. But the type checker is going to be reviewing it and doing some clever things under the hood to track what's going on. So this is where it may start to get interesting. Flow supports unions of types. So you can read void as undefined here. So this is saying that there's a type called name, and it's either going to be a string or it might also be undefined or null. This is really common in JavaScript. It might be a property in an object that may or may not be there, or an optional parameter passed to a function. It's so common that there's a shorthand for it in both TypeScript and Flow, where you add a question mark before the name of the type, but it means exactly what you saw in the previous slide. So we'd call this a nullable type. This is a nullable string. Union types, from the type checker's perspective, union types exist in this sort of quantum state, where it could be any of them. So in this code, we might think, oh, well, now we can see that foo definitely has a value. But since we've explicitly told the type checker to treat it as a nullable string, it's going to pretend, at least in this small example, that foo could be null. So if we try to interact with foo, try to modify it, we can do or pull data off of it. We can do the things that are common to all the types, which in this case, null and undefined, don't let us really do anything. So if we try to treat this nullable type as a string and ask for the length, the type checker will let us know that this isn't safe. This is gonna blow up on us when we try and run our code. We're gonna get length is not a property on undefined. So our type checker is actually being helpful here. But if we check to see that the variable foo is truthy, then the type checker knows that inside this block, that the only type that is in that union that's going to evaluate as true is going to be the string. So it knows that within this block, that foo has to be a string, so that when we try and take the length of it, it works out just fine. So when people refer to Elm as having no runtime exceptions, that comes at a cost. And it doesn't come for free. So the language will force you to be a little bit more disciplined and to take all of these things into consideration to make these checks. So there's another feature of Flow where instead of saying something is a string, we can be a little bit more specific. In this case, we're saying that currency is going to be one of these two particular strings, these two constant values. This creates an enum. Anything with this type can only contain these two strings. And this is sort of an example of a type that can't be inferred. Like if I'm assigning USD to a variable, Flow is going to think I'm assigning a string. But I can be more specific, and I can declare my intent to the type system. There's also an object type. But if you use just a plain object type, the type system is not going to know anything about the contents of the object. So you basically said, I have a box. And I can take anything out of it and put anything into it, and the type system is just going to have to assume that you know what you're doing. But the type system becomes much more useful to you when you start to define the structure of the object. So in this case, we were saying the type price has both a value, a number, which has to be there. It has to be present, and a currency, which can either be US dollars or Canadian dollars. So if we try to assign something that doesn't match that type, here for currency, we've decided that we're going to go with pesos. Flow is going to catch that, and it's going to say that, no, this actually isn't a valid type. So if we add a new option to the enumerator, and we now say we support pesos, then the type checker says, OK, that's all good. We can even compose these two features in something called a disjoint union. So we're using object shape, and we're using a union of types at the same time. A disjoint union is going to require that all of the shapes we're deciding between contain this common property that the type system can use to distinguish between them. Usually it's a specific string with a name. Here we're just using a Boolean. So the type system can then use this tag to do refinement, just the way we saw with the null checks. Within this callback, result is in the same quantum state we saw with the nullable string. Here, the type system knows that if result.success is true, then we can see up in the type declaration that result has to be a number and it has to be present. So then this works. But if we try to print out the error property, which is in the false branch, then the type system knows that this isn't present. And so it can warn us that, hey, you're trying to access something, or your logic is wrong, or you should probably review this. And that's kind of it. That's, at a high level, that's all the features we're going to talk about today. And there's a lot more to Flow's type system, and there's a whole lot more to TypeScript as well. But these few features pack a very large punch. They kind of punch above their weight class when you know how to use them. So we're going to see how this might play out in a concrete example. We're going to pretend that you're building a store app in JavaScript. And as a ploy to keep your attention, we're just going to say it's a candy store because who doesn't like candy? So every item has a price, and you need to calculate how much that item costs given how many are being purchased. So that's simple enough. You just multiply the number that we're buying by the price, and that's it. You ship it. But we know this won't stay simple for very long. One, because I've conveniently left a whole bunch of space on the slide. But we also, just in spirit, we should never expect our software to stay simple. Software doesn't exist for the purpose of being simple and elegant. Like, it exists to serve a function. It exists to serve a business. And that's natural that that business is going to grow and change over time. And then so our code is going to have to change along with it as the business evolves. Now, there's going to be a good bit of code on this slide, on the next few slides. But don't try and understand it. Don't try and follow it. Just watch how it's evolving. So we shipped the first version of the store, and it's a great success. Everyone's walking down the sidewalk with big chocolate bars, and it's a beautiful thing. You've created something of value in the world. But then the owner of the store goes to the airport, and they see the bulk bin candy section, and their eyes are open to the possibilities. So we have to have this in our store. This is going to take us to the next level. Let's implement this. So now an item has another thing it might have. It could have a price per unit. And it's either going to have a price per unit and be a bulk item, or it's going to have an individual item price. You can't buy an individual jelly bean. So there's just one branch, and that's not so bad. Then the store decides that they want to run a sale. And that's kind of a reasonable thing for a store to do. So you have 10% off lollipops and 20% off chocolate bars. And we have to add a new case. So there's just one more case, and then just another else statement, and that's OK. Then the sale was a success. We saw profits go up, the business is booming. So let's try another one. So now it's buy two, get one free on rock candy. And that's a little bit more complicated, and this is starting to become a little bit unwieldy. Now we're probably writing tests in order to make sure that we're not messing this logic up. And then yet another requirement comes down. Another candy store opens down the blocks, and so now we want to try and make sure our customers are loyal to us. We want to give them membership and discounts on individual items and bulk. So we have special prices, and this is sort of where I stopped trying to make an example. It's just the code had this explosion of complexity. I'm not really willing to write this code unless I have a test suite. And there's a good chance that if you try to write this, you're going to apply the discount to the wrong thing, or you're going to miscalculate a price, or you're going to ignore a member price and you're going to charge the member too much. And worse, this object is probably not used in just this function. It's going to be accessed across our code base. We need to know if an item has a discount to advertise that discount to non-members. We need to know if a special applies to an item to maybe brand it differently, to maybe have a 2-for-1 sign. And this is making it harder and harder to make changes. Once we make a change in this function, we also have to make sure that's consistent with the rest of our code base. And our code base could be millions of lines of code. It's getting difficult to understand what an item really even is. And it's not going to stop here. Like, the business is going to continue to grow and change as things are being successful. You're going to maybe support multiple currencies. You might add a new level of membership where you have an elite membership that has deeper discounts. These are all reasonable features for a shop to have. And so we can expect this to keep growing and changing, and we need a better strategy to deal with that complexity. So if we look at the type for our item, we can start to see maybe some issues. One, every single property in the object is optional. It may or may not be there. This means that someone can pass in an object to our function that doesn't make any sense. Like here, there's a member price, but there's not a normal price. Does that make any sense? I mean, if it has a unit type, but why? And then do discounts even apply to bulk items? But our type system is going to say, oh, that's cool. Like, it matches the declaration. A-OK. Or what if we assign a discount where it doesn't make sense? Here we have a bulk item, and maybe someone made a change to the discount code, and now we have a 2-for-1 special on a bulk item. Does that mean that at the counter I'm counting individual jelly beans and separating them? That doesn't really make a ton of sense, but the type system is OK with it, so let's just go with it. And then even worse, since every single property here is optional, people can pass it in just a completely empty object, and it doesn't send up any red flags. It's fine. So how many times have you been debugging something crashed in prod, and you get you log out an object and you're just like, how did that happen? And then you're kind of in this quandary where you're forced to play computer in your head and go, okay, well, what are all the places that could have created that object? And or you just litter your code with log statements and hope that you can hit that case again. So, and worse, in this type system where you have nullable types and it forces you to check, trying to write code against this type is going to be really, really painful. You're going to have to check to make sure it is an actual value all over, and you're going to litter it with these if statements. And then if it is null, what do? You throw an error. It's hard. And so the type system is sort of gently encouraging us that we need a better solution, a better strategy. So if we take a cue from OCaml or Elm or some other strongly typed languages, there's this piece of advice for cases like this. Make illegal states impossible. Try and use the types to define your object in such a way that it's actually impossible to represent a case where it doesn't match your business logic. So we should explore what we can do here. We have the type, but there's a whole bunch of relationships between these individual properties that we honestly just can't see here. So price and member price, we probably shouldn't have a member price without a price. So there's a relationship there that's not being expressed. We shouldn't have a price per unit without a unit type. And then while we're at it, we should probably actually enumerate the different unit types that we support so we don't accidentally charge someone for pounds instead of ounces and lose a whole bunch of money. And then what discounts even are there? Can an item be both on sale and priced at buy two, get one? Maybe both are valid choices. It just depends on what the use cases for your business are. But we have to apply that consistently in every place of our application. So we're going to go back to Flow, and we're going to try and sort this out. We start out with just a price, just like before. And now we can use the disjoint unions. We have an extension point. So now we're saying something is either a single item or it's bulk pricing. And now we can see that a single item has to have a price, and bulk pricing has to have a price per unit and a unit type. Nothing is nullable, nothing is undefined, and it makes writing the logic for this actually pretty simple. We're just switching on the type. And then we can conveniently add membership prices. Now you'll notice that they have a question mark. They're nullable. So this is the programmer that's writing this is now expressing the intent that there may or may not be a member price for each item. But now it's documented in code. And then here we have an enumeration of the different types of discount. We have a percentage that requires a value, and then we have 2-for-1, which doesn't actually require any additional data. It has also become clear that now we can add new discounts. We just add another case, and it becomes clear where we can extend the logic. So if next week we have a new requirement, we know that we can come back and we can just continue modifying this and add more information. So best of all, if someone tries to build an object that matches this type with some parameters that don't make any sense, so in this case we have a member price but no price, the type system is going to check that. So it's actually now impossible to represent the price info object that matches these criteria that doesn't also make sense for our business. We've just completely eliminated a class of problems. And the additional structure means that writing a function like calculate price is a lot more straightforward. And if we mess up and try to apply a discount to a bulk item, the type system is going to let us know that, hey, you're trying to do something that doesn't make any sense. So that's really cool. But I want to call out that we didn't have to make any classes. We didn't have to inherit anything. We didn't have to draw a diagram with a whole bunch of boxes. This is just a little more than a dozen lines of code. And it also serves really well as documentation. This is probably written down somewhere anyway. And it conveys intent. But it enables the type system to do a lot more for us. So there's another idea I'd like to talk about that comes from these other languages. I was first introduced to this idea when I started reading about Rust. But it was in OCaml before that, and who knows where that came from. If you have maybe deeper knowledge, I'd love to have a more nuanced understanding of that history. And the idea is that we should structure our code in such a way that the type system can tell us when we're missing something. So this is Rust code. And Rust has idioms as a first-class structure. And it has a match statement that allows you to destructure on that enum. And it works kind of like a switch statement in JavaScript. Instead of using string values, you can use the enums in the language, and we can match to branch on the value. But there's an important difference in how this works versus how a switch statement works in JavaScript. If the match isn't exhaustive, so here we've forgotten a possibility. There is a blue color, but we don't have a branch for blue. So we're going to get an error, and it's actually going to tell us exactly what case we're not covering. Elm in particular has really good error messages for this situation. Now we can make it harder for the type system to help us. So in Rust, you can use an underscore to basically have a default branch. It says anything that doesn't match any of the above statements should go here. But if now we modify the color to add a new statement, crimson. So we're either printing red or not red. And blue and green are definitely not red, but crimson probably should be red. But now the type system is silent. It says, well, this logic makes sense, because it doesn't understand our intent. So now we've sort of made it more difficult for the type system to help us. But if we exhaustively list the possibilities, then now our type system can help us again. And it knows that, oh, you actually haven't covered this one case. So the strategy is to always write your code when possible, to exhaustively list all the possibilities so that your type system can be more helpful. So if we go and try the same thing in JavaScript, it doesn't work. So here we have red, green, and blue, and we have cases for red and green, but no blue, and the type system is just fine with it. So that's rather sad. It turns out that neither Flow nor TypeScript support this, support exhaustive matching, at least so far. But you can hack it. So Flow has a special type called empty. Empty doesn't satisfy any types. It's impossible. And TypeScript has an equivalent type called never. It looks almost exactly the same. No type satisfy empty, so we can add it as a guard. Here we're saying that in the default case, the type should be empty, so no valid type should ever hit this branch. And when we add this code, voila, we get the error message that we want. It's not entirely equivalent to something you would see like in Elm or Rust, because it won't alert you to the fact that you have unused branches or things like that. But it's still incredibly useful to structure your code this way. So let's go back to our candy store. And we decide to offer machine rentals. So cotton candy machines are always a hit at children's parties, at least for the guests, maybe not so much the parents. And now we have a logical place to add the data. So we're returned to the pricing info from before, and we just add the data. We add the new type. So now we have single items, we have bulk items, and now we offer these machines for rent. And there was an easy point to add that extension. And now we get errors. So looking at the calculate price function that we were working on before, we now see that, oh, we have to deal with this new case. And more importantly, we're going to get a lot of errors all across the code base everywhere we're accessing this object, because we've designed our system to be exhaustive. So now the compiler is raising an error, but it's really kind of like a helpful tip or a pointer saying, oh yeah, by the way, to make this change work, you also need to update all of these other files. This is like a very, very helpful pair programmer who has the whole system in their head, and I don't have to. I can make the change and be like, well, does this work? You tell me. So the compiler is being helpful. So you could think of it as, errors are just the type system's way of saying, I love you and I want you to be happy, and you should probably go update that. This was something new to me. Like, I was used to a compiler or type system sort of being like the final step. Once you have done all the work and implemented the feature, then you have to go and maybe spend minutes, but maybe hours fighting with the type system. This is the first time that I'd had a type system come and it was my friend. It was helping me. So that's my talk. If this is interesting to you, I highly recommend watching this talk called Effective ML by Yaron Minsky from Jane Street. They use OCaml a lot in production. I basically took the ideas from that talk and reframed them in JavaScript, but there are a lot more in the talk. And it's in OCaml, but I don't think you actually need OCaml to understand the talk. And thanks.